Hello. So as said, I'm Hanno Böck, and I want to talk a bit today about how you can find bugs in your software, especially if it's written in C or C++. And some very powerful tools that I think not enough people know about yet. But first, a quick introduction about me. So I once worked as a freelance journalist, and I often write for the German online magazine Golem. I also write a monthly TLS newsletter, and now you can see that sorry, these are the wrong slides. I did almost the same talk a couple of days ago, so I write a monthly TLS newsletter. And I run the fuzzing project, which is something I founded about 2 years ago, and which is funded by the Linux Foundation's Core Infrastructure Initiative, where I try to reduce the number of bugs and security vulnerabilities in free and open source software. So here's an example, and it's from Qt. There's a problem with this code, and so what's actually happening here is we have some kind of array structure, and we have an iterator pointing on it, and there's a check here that if we're at the last element of this array, then it reduces the pointer by 1, and therefore we're pointing to one element earlier. Now the problem here is, if we have an array with only one element, then we're trying to get to the previous element, and then we're in invalid memory that's not allocated. So what happens here is the code reads some invalid memory, and then something weird may happen. This is a real bug in Qt. I have actually not reported it yet because I discovered it yesterday while I was on a ship without Wi-Fi. So sorry, I have not been able to report it yet, but I will report it. I found plenty of bugs in Qt and KDE. So I found a use after free bug in QMake, which is kind of the build system tool from Qt. I found this bug I just showed you, and I found several out-of-bounds reads of similar kind in Qt GUI and also in Kwin. For the last two, I'm not entirely sure who I should blame, because the code is using the X API in a wrong way. But I think the X API it's really strange how it behaves, because it asks you to use a struct but then you need to allocate more memory for the struct than the size of the struct, because it tries to read a certain size from it. So I'm not entirely sure. Maybe there's a way to fix this in the X API. I have to look into this. And to be fair, I also have to mention GNOME. I found a bunch of very similar bugs in GNOME, for example, 2 bugs in glib, which were out-of-bounds reads, heap overflow in GNOME session, which is triggered actually every time you start GNOME, an out-of-bounds read in Pango. Here's this heap overflow in GNOME session. So what's happening here is that there's an allocation for a buffer that contains a list of pointers, and it contains all the pointers from argv plus 3 more pointers. So can you see the problem with this? Who sees the problem with this? One person, that's nice. So the problem here is we add argc plus 3 and then times the size of the pointer. But there are brackets missing around argc plus 3. So what we're actually doing is doing 3 times the size of the pointer plus argc instead of the other way around. So it ends up we have a allocation that is too small, and it's a very classic buffer overflow. And as I said, this buffer overflow happens every time you start GNOME. Why are there all these bugs, and why don't people seem to find them? There's a tool that I want to suggest that you all should use if you write code, which is called Address Sanitizer. Because all of the bugs I just showed you and mentioned can be trivially found with Address Sanitizer. And this is a feature which is part of the GCC and LLVM compiler suites. So it's basically just a flag you add during compilation. So you add fsanitize address to your compiler flags, and then you get this feature that will analyze these kinds of bugs for you. So this is how, if you have a project that's written with auto tools, this is how, and if you have a test suite, which some people have, and then this is how you would run your test suite with Address Sanitizer enabled. So it's basically you pass some C flags to your configure flag, to your configure script, and some C++ flags and some linker flags. And then you compile as you usually do, and then you run your test suite. So I think we can agree that this is not too hard. Like, if you're developing code, like typing in these 3 lines, it shouldn't be too hard. But apparently it seems like several people have never done this before. There's a question?
I just wanted to say that in KDE, our CI does use those flags, so we sometimes find some of the mistakes.
Okay, so
the thing is that we're missing more tests, so that we would.
So what I just heard is that KDE is already doing this in their CI system, but you probably never start KDE with these flags, because else you would have found all the bugs I told you earlier. But these were all found by just starting KDE with these flags. So yeah, but it's good if you do this. That's great. Thanks, GNOME doesn't do it, so good. So how does this async thing work? So what Address Sanitizer does is it reserves an amount of a so-called shadow memory, where it tracks for each byte whether that's allocated memory or not. If you do a memory allocation, it marks this as valid, or if you create a stack with a function call, but it also makes sure that between the allocated space, there's always some so-called poison space. So if it changes the stack layout, that between variables, there's always some poison space, so it can detect when you overrun a buffer, no matter if it's on the stack or on the heap. And the most common bugs you can find with this are out of bounds and use after free. There are other kinds of bugs it finds, but these are the most interesting because they are very common. And also, like, use after free bugs are the most common security bugs in complex pieces of software today. So especially if you have something like a browser, then usually the memory corruption issues there will be use after free. So this is an out-of-bounds read access. Relatively simple code. So we have an array with 2 elements. Then we create an integer which we assign 2, and then we try to access element with the index 2 of that array, and as arrays started counting by 0, 2 is invalid, we only have an element 0 and an element 1. So I have this code here, and now if I compile this without anything special, then I just see some garbage number printed out. Because, okay, it's reading some invalid memory, and there's something in that invalid memory, and it just prints that out. Okay. Now we add Address Sanitizer, and we add G, because then we have debugging information, and that gives us a better stack trace. That's just the reason for it. And then we run this, and then I have to unset this variable, and then we run it again. And then we get this very nice error message. So it says a read of size 4, because it's an integer, it's 4 bytes. In line 5, column 17, and it also here says that, okay, the address is located in the stack of the thread that's generated here, which is our main function. So you run this code with Address Sanitizer, you hit this bug, and the program terminates, and you get a very, very detailed error message. So if you know your code, you should be able, by reading this error message, to figure out what's wrong. And this is a use after free bug, a very simple example. We're allocating some space with calloc, so it's initialized by 0. then we print some element of this array, and then we free that, and then we try again to print something. So that's now invalid because we just freed this buffer, so we should not read from it anymore, but we still do. So I have this code here, and the same if I run this with Address Sanitizer. And for use after free, the very nice thing is it tells me basically 3 important things. The first is, okay, here is the use after free access. Then here's where this stuff got allocated. And here's where it got freed, because like these are the 3 pieces of information you need to analyze a use after free bug. So yeah, also very nice. Of course, these are extremely simplified examples. You will have much more complex examples in your code, but that's the basic idea is always the same, what a use after free is. So I kind of got this, I saw, okay, there are these many bugs you can find with Address Sanitizer, and I made it kind of my mission to like test everything with Address Sanitizer and fix all these bugs. So what I did was actually, I started building a Linux system with Address Sanitizer, like with everything except a very few core packages where it's more difficult built with Address Sanitizer. And it runs. I can run it in a VM, or I even have a server where it runs. Just by doing that, just by trying to create a Linux system with Address Sanitizer enabled, I found bugs in things like Bash, core utils. Man, Pigeon OTR is kind of security sensitive. I don't know, maybe this is important. Yeah, and also Qt and KDE, so we're at QtCon here. And many other things. So basically just by compiling stuff with Address Sanitizer and then trying to use it. One more thing. When I did this, I thought this may be something I would recommend as a kind of special hardened system for very security sensitive things. But it turns out this is not a good idea, because Address Sanitizer is not designed to be a security tool. It's designed as a testing tool. And if you do this, you end up having security vulnerabilities introduced by Address Sanitizer. For example, if you have suite binaries with Address Sanitizer, you can basically use the error message functionality and let it dump files with root permissions, and then you can get root with that. So it's a good thing to find bugs. Great to test things, but it's not good for production use, at least not in the way it's implemented right now. Maybe there can be some future Address Sanitizer++ that's usable for production, but not the current version. It's a testing tool. And like the overhead is, you have like 50% CPU overhead and quite some memory overhead, because this shadow memory takes quite some space. So yeah. And now I want to get into the next topic, which is fuzzing. So fuzzing, the idea is very simple. It is you take some invalid input and test the software with it. So the very thing I'd like to phrase this is you throw garbage at software and see what happens. So in practice, if we take a simple example, like we have an image parser and we want to test it, then we take a valid image like a JPEG or a PNG, and then we just add random errors to it. Like we just add in some characters, flip some bits, delete something, whatever, swap parts of it around. And then we test if that crashes the code we're trying to test. And who of you has heard of the DARPA Cyber Grant Challenge recently? So quite a few. So here are a bunch of press articles about it. So watch AI hack into AA at DARPA Cyber Grant Challenge. AI hackers will make the world a safer place. And also Elon Musk says DARPA AI hacking challenge will lead to Skynet. So the general theme of these articles was, okay, there are now some AI bots in computers in some shiny glowing boxes, like on the lower left, that's a picture from DEF CON where these boxes were like on the stage, and they are hacking each other and automatically finding vulnerabilities, patching them and exploiting them. And then by that, they are basically trying to replace security professionals with AI bots. So they want to replace people like me with an AI bot. And then these AI bots at some point, of course, will create some Skynet and suppress humanity, and we will have some Matrix kind scenario. So if someone wants to replace me with an AI bot, I mean, I'm cool with that. That's, I mean, totally fine. I will find something else to do. But I would like to understand what's going on here, right? So I'd really like to understand this. And all these articles were like very shallow. I didn't get any technical details of what's going on here. Here's a PR video. I'll not show the whole video, but like some parts of it. Here you can see the fancy, colorful things on the DEF CON stage.
Game started at 0900 and 45 seconds Pacific.
Welcome everyone to the first ever fully automated cybersecurity automated competition.
Sandra managed to discover and prove a vulnerability in one of the services that we call OpSim, but this is a unique situation and it's something we were kind of hoping to see. They actually managed to discover an unintended vulnerability. So each of these services that's written, just like real-world software, it's impossible for us to have made absolutely certain that the one vulnerability that we intended is the only one that's present. So the discover this vulnerability and actually begin trying to prove that vulnerability against other teams or other bots very, very early on. So this represents a true success to what we have going on here, because in that 5-minute window that Deb mentioned that she was hoping for, that actually managed to be proven and patched by several of them. Basically represents a leap forward in programming.
I want to go to this.
I mean, all the talk about state machines and all the possibilities of state machines really reminds me of one of the papers that we published recently. We published the paper Driller, which is supposed to augment fuzzing with symbolic execution. And
did you hear it? He said fuzzing. So, okay, at this point I thought, okay, this is something I know something about. So, yeah, okay, so maybe, yeah. Because, you know, if people talk about artificial intelligence these days, I don't know how you feel, but I get extremely skeptical. I think a lot of stuff is called artificial intelligence, which isn't really anything about artificial intelligence. And, well, okay, so this seems to be about something about fuzzing. And I talked to the leader of the winning team, David Brumley, and he told me, okay, they are using a tool called AFL, or American Fuzzy Lob. And immediately this became something I'm very familiar with because I use it all the time. And then I learned not only the winning team, but basically most of the teams were using American Fuzzy Lob. The first place, the second place, and the third place all were using American Fuzzy Lob. So basically that's the real winner of this competition. Is it AI? We can argue about the question was, is American Fuzzy Lob is AI? I don't know. I don't think AFL is the Skynet, but it's pretty smart, so maybe it's some kind of AI. Yeah. So this rabbit is an American Fuzzy Lob, but it's also the name of a tool. And to understand what American Fuzzy Lob does, I want to go a bit into like what different strategies there exist for fuzzing. So the very original idea is what I would call dump fuzzing, where you only add errors at random to an input and test it. So that's easy. It also, I mean, it's surprisingly effective already. So you already can find a lot of bugs with it. But it's not going very deep into your code. So if you have some complex issues, it won't find them. And then you can do something which I call template-based fuzzing, where you write a fuzzer that's specific for a certain data structure. So you could do something like you want to fuzz an image parser, and then you try things like, what happens if I put a 0 into the width, because that doesn't make any sense. So let's see if the parser correctly handles that. The problem with this is it's a lot of work, because you have to do it for every data structure you're fuzzing. And therefore I say it doesn't scale. If I want to fuzz all the software out there, I will never be finished. And this new thing that came up with AFL is what's called coverage-based fuzzing. And what this is doing is that you're adding some extra assembly instructions during the compile step. And these allow the fuzzer to learn something about your code paths. And when you have an input to the tool that triggers a new code path, then the fuzzer sees, okay, this is generating something interesting because now we're triggering new code. And therefore, we should continue fuzzing with this as a starting point. And this leads to some pretty impressive results. So there's a blog post by Michael Zalewski, the author of AFL, where he started to fuzz a JPEG parser with garbage input. And after some hours, it created valid JPEG files. So maybe that's already kind of Skynet thing. I don't know. It's at least pretty impressive. So yeah, so AFL made this idea of coverage-based fuzzing possible, and you work in 2 steps. First, you compile it with the AFL wrapper compiler thing, and then you start the fuzzer. So, and to show you also that this is really easy, yeah, you run like still auto tools based, but you run configure, you pass CC and CXX so that you run it with this compiler wrapper. Then it's always a good idea to disable shared libraries, because then you don't have to fiddle around with LD preload and anything. Then you build it, and then you need some kind of sample file that you want to fuzz, put it into a directory, which I always call in, but it's just an arbitrary name. And then you run this fuzzing process, where you put the input directory, output directory, and the path to the thing you want to fuzz. And then you add this add, and then the fuzzer will call this executable with and pass the file that's currently tested at this add position. And this is how it looks. So nice ASCII art interface. The most interesting part is the upper right corner, because there it shows you the number of unique crashes. That's a bit of a lie, because you will have duplicates there. The detection of unique crashes doesn't really work, but it tries to err on the side of caution. So, and it also detects like hangs if you're stuck in an endless loop or something. And the number of paths it detected. And that's also important, because if that number doesn't change, if it stays at 1 or 2, then probably something is wrong with your setup, and you should check that. I'm inclined to say AFL probably found bugs in every single important piece of software that's written in C. So in OpenSSL, OpenSSH, libJPEG, libPNG, SQLite, GNU-PG, Bash, StageFright. StageFright was the Android thing that made some headlines last year. Yeah, so really a lot of bugs found with AFL. There's a list on the web page that's quite impressive. So it made a huge impact like on bug finding in the free software world. And so I now told you about AFL and Address Sanitizer, and there's a very obvious thing to do, and that is to use both at once. Because Address Sanitizer finds these additional classes of bugs that are hard to find otherwise, and AFL is a very good fuzzing tool, so you can just use both at once. What you have to do is basically, AFL already has a feature built in for that, which you can enable with an environment variable, AFL use ASAN. You then need to disable the memory limit from AFL, because Address Sanitizer has this thing that it allocates this shadow memory. And it is only a virtual allocation, but it's several terabytes. So it's only virtual memory, so it doesn't really use that memory. But if you put a memory limit on it, it won't work. Therefore, you just need to disable the memory limit. This can, of course, cause a situation where you have an application that uses a lot of memory and everything will crash. But in my experience, that almost never happens. But that's the reason why AFL has a memory limit in the first place. So, simple solution, just disable the memory limit and you're done. Okay, who remembers this logo? I hope everyone. This was the Heartbleed bug, probably the most famous bug in any piece of code ever, made headlines everywhere. At some point I was asking myself, okay, could we have used fuzzing to find a bug like Heartbleed? And I have to say here, okay, one of the people who found Heartbleed actually used a fuzzer, but it's a proprietary tool that's specifically targeted to TLS, so it's not kind of a generic fuzzer. It is what I earlier called template-based fuzzing, and it's not free, so I cannot test it. So, but I wanted to know, like, can I use the tools that I use for fuzzing to find a Heartbleed bug? And okay, one problem is that American Fuzzy Lob is file-based, and this is kind of networking. So, but the OpenSSL API has a nice feature that I can basically do a TLS handshake without really doing a handshake. I'm just passing buffers back and forth. So I have two instances of OpenSSL and let them talk to each other, but without any real networking involved. And then I could like write something that I just swap one of these handshake messages with a file that I pass on the command line. And doing this, after 6 hours, I was able to rediscover the Heartbleed bug. And then I got an email from Kostya Cerebrani, who is the developer of Address Sanitizer and a couple of other things. And he said he has this tool called LibFuzzer. And it's able to do the same thing, but in 5 minutes. So that's also quite impressive. And LibFuzzer it's modeled after AFL, but it works a bit different. So where AFL is working on executables, LibFuzzer is working on functions. And that's much faster because it's faster to call a function than to run an executable. But there's a downside to it, and that is you have to write code to actually use this. And because the big advantage of AFL is that it's just so simple. And with LibFuzzer, you need to write code. This is an example for fuzzing an OpenSSL function with LibFuzzer. So we're basically writing a wrapper function here that gets a buffer passed and the size of the buffer. And then I'm just calling this OpenSSL function, which is called ASN1 MB string copy. I pass this buffer. And then very important here is that I check if it succeeded, and if it succeeds, then I free the structure it generated again. Because if I don't do this, then I have a memory leak. And as it's running this like millions of times, the memory leak will add up, and at some point I will run out of memory and my fuzzer crashes. Therefore, if you use LibFuzzer, keep in mind you have to write a wrapper that's free of memory leaks. Yeah. Then something, what's also an interesting method is what's called differential testing. So the typical fuzzing scenario is to look for these kind of memory safety issues and crashes. But you can also do other things. And if you have a function that has a clearly defined output, then what you can do is take two different implementations of the same thing and then compare the result. And some area where this works really well is mathematics. Because if you have something like an exponentiation or a division, then we can agree that this has a clear result. I mean, there's no discussion like 2 times 2 is 4 and not something else. If two implementations disagree on some mathematical calculations, then one of them must be wrong. Yeah. At least one of them must be wrong. Yeah. I didn't run into a situation where two were wrong in a different way at the same time, but maybe that happens. And there was a bug in OpenSSL in a function called bn square, which is squaring. So you multiply a number by itself. And in very rare cases, this function would produce wrong results. And these were so rare that it was in 1 out of 2 to the power of 128. And this number is so large that if you use this function with random input, you can do this for your whole life and it will never hit this bug. So it's a very rare bug. But the surprising thing was American Fuzzy Lob was able to find this bug. So maybe this is another indication that there's some Skynet thing going on. I don't know. The first person who showed this was Ralph Philipp Weinmann. He had a talk about big num vulnerabilities at Black Hat last year. It's on YouTube and I recommend watching it. It's very interesting. And then I tried this, and AFL is really good at this. So I found a bug in OpenSSL in the modular exponentiation. This is the function that's basically RSA and Diffie-Hellman, so kind of important. Unfortunately, nobody found a way to exploit this, but it's still, I think it's something where you should look into that it's correct. Then in the elliptic curve code from Nettle, which is used by GNU-TLS, also in the modular exponentiation of NSS, in the Poly 1305 authenticator in OpenSSL, this has no CVE because this was never released I found the bug before they released the code, so yeah. And in Matrix SSL, which had the interesting property, if you had a 0 to the power of something, it would crash. And then I thought, okay, I can do this over the network. I just sent them an RSA signature that's 0, because then it will try to exponentiate it and crash, and that worked. So, yeah. And also, like, there were situations where it produced wrong results, and they haven't really fixed all of that. Yeah. I wouldn't recommend using Matrix SSL. Yeah, so one of the things I run into when I do these things is the vast majority of bugs. I mean, with these bugs, there's no discussion. These are bugs, and also usually people agree that this is a security vulnerability. But if I found something like an invalid read access on the heap for 1 byte, which happens extremely often, then people tend to argue, is this a security vulnerability or not? And I find these discussions a bit pointless because I say, okay, it's clearly a bug. I mean, you're reading invalid memory. You cannot do this. So I say, okay, can we just like skip the discussion whether we call this a vulnerability or not? I simply don't care. I want you to fix this and we're done with it. So I think in many situations, it's just easier to fix the bug than to have the discussion on how severe this is. Yeah. Then I want to mention a couple of more tools. So this Address Sanitizer, there are a couple of other sanitizer tools. I just think Address Sanitizer is the most interesting. There's Undefined Behavior Sanitizer, which finds many small things that the C standard says are undefined. And that essentially means if you do these, you cannot have any expectation of your code that it does anything reasonable. It can just do whatever it wants. The compiler can optimize it in a way that if you do this, you cannot expect it to do anything sensible. There's Memory Sanitizer, which finds uninitialized memory. Problem with that is it's nice, but it's tricky to use because you need to compile all the libraries you use with Memory Sanitizer. And if you do C++, even the lib standard C++. So that's a bit of annoying to use. And there's Thread Sanitizer, which is mostly... There's a question?
Just a comment that same thing you just said is valid for Address Sanitizer as well. So if you don't compile libc++ with ASAN, you won't be able to find bugs that are triggered within libc++ by your code. And it's the same for why you should
that is true. That is true. But you can still use Address Sanitizer to find bugs in your own code and not in the standard C library. While if you try to do this with msan, you will just get random false positives that make no sense at all. So the difference there is you get better results with ASAN if you compile everything down to the last library with it, but you can still use it if you only compile one thing with it. Yeah, and there's also Thread Sanitizer, which is like mostly interesting for large projects like browser. For KDE, it's probably also interesting, but yeah. So here's an example for ubisan. What we're doing here is we're shifting the variable by j, and j is -1, and that's invalid. You cannot do a shift with a negative value. That's undefined. And the next thing here is an integer overflow, which is also undefined. And I have this code here as well. And the difference here is that ubisan doesn't terminate your application, so you can find multiple bugs at once. And the latest version of ASAN is also able to do this. But you see here, shift exponent -1 is negative, signed integer overflow. And here's an example for Memory Sanitizer. So we have an array here, and then we set element 1. And then we access element number of argc, which is by default 1, but if we pass a parameter, it's more. So, so if I run this, I don't get an error, but if I pass any random parameter, I will get this, yeah. use of uninitialized value. Okay, then there are a number of these tools also available in the kernel. So there's a kernel address sanitizer, kernel ubsun, kernel tsun, and there's a fuzzing tool called syscaller, which is trying to adapt this coverage-based fuzzing to the kernel space with syscalls. I'm not super familiar with those. I just once tested KASUN and it found a bunch of stuff in my GPU driver. Then one kind of biggie is network fuzzing, because nobody really found a very good solution for that yet. So you run into a lot of trouble like trying to do this, because you kind of need to define like when you're basically you need an application that terminates after one connection attempt and things like that. And there's a tool called Preeny, which is trying to put a file and then simulate the networking calls and like let the file look like it's a TCP stream. And there's a patch to AFL which tries the same, but all of that is pretty fragile and doesn't work very well. So I haven't seen anything there yet that works as flawlessly as the file-based things, and that's something I would like to see. But we're not there yet. Then there currently seems to be some research interest in combining fuzzing and something that's called symbolic execution. So symbolic execution is basically comes from formal software verification, and the idea is that you're basically trying to analyze a piece of software and analyze all kinds of states the software can get into for all kinds of inputs. And the problem with that is if you try this on any real software, it will just have so many states that it will never finish running this analysis. So what people are trying to do is to use fuzzing, and if the fuzzer is stuck that it cannot reach a certain part of the code, then they try to use symbolic execution for it. I am kind of looking forward to see whether this will work or not. Some people in the DARPA challenge have done this. But there's nothing there yet that you can just use and try out. So there's one thing has been published, which is called Driller, which the guy you saw earlier in the video was talking about. But it is like for a artificial operating system that was used in the DARPA challenge and not for a real operating system. Therefore, it's kind of questionable how this translates to real. So this is like open research and we will see. But I must say I'm a bit skeptical if this is really something that will lead to significant, interesting results. What I want to say, like all of the tools I presented to you are free. Unfortunately, not everything that the DARPA challenge made is free, which is kind of a pity. But AFL, LibFuzzer, Address Sanitizer, all the other sanitizers, it's all free software. So there's essentially no reason not to use it. So just use it and fix your software with it. And now this is something that kind of came up in the past couple of years. What I'm doing here is mostly fixing bugs in C software, which are typical C problems. And you know, there are these people who've been saying since forever that we should just rewrite everything in some safer programming language. And this debate has now accelerated because there's Rust, and a lot of people like Rust. And I think this is, I'm not joking here. I think this is a serious debate we should have, whether this is really the way to go to try to fix all these C bugs which pop up again and again, or if we shouldn't like move to something safer. So, but I mean, this is also kind of questioning of if what I do is the right thing to do. So, yeah. But I wanted to have it mentioned, and maybe someone wants to rewrite Qt in Rust. That would be cool. Okay, so and finally something. Is anyone here working for Red Hat? No, that's sad. Anyone working for Debian or like involved with Debian? Okay, so you will be happy. So I thought, okay, I will fuzz package managers because like why not? They pass stuff and then that's good for fuzzing and I can test if they have sane code. So I fuzzed dpkg and I was impressed. So I reported 2 bugs to the Debian security team And 8 days later, there was an update and a security advisory with these bugs fixed for both from Debian and Ubuntu. So that's pretty good, right? I mean, if you have a vendor reaction like that's cool. Then I fuzzed RPM. So in November last year, I reported 3 bugs in RPM parsing to the Red Hat security team. I got an answer, yeah, we just got 30 crash reports for RPM. It may take some time till we tackle this. Okay, a bit about RPM. I mean, RPM is, it was originally the Red Hat package manager, but in 2007 they decided to make it an independent project. It's now the RPM package manager. It's used by Red Hat and SUSE and some others. So it's kind of independent, although, I mean, rpm.org still belongs to Red Hat. So, but the Red Hat security team says, however, we don't own rpm.org domain, so they disagree with the whois data. I'm not sure. rpm.org is a track installation. Track has a bug tracker, so I could report bugs there. That's great. But then I tried to register an account and I got a certificate error. It was expired in 2012 and it didn't match the domain name. But then I ignored the certificate error and created an account anyway. And then I found out, okay, I still cannot create a bug. It tells me I should ask on the mailing list or on IRC whether I'm allowed to create a bug. I mean, and then in the communication with Red Hat, I found out, okay, there's a GitHub repository, but there's no link on the web page to the GitHub repository, which is, yeah, I don't know. And then, okay, maybe you want to find out what's the latest version of RPM. There's some disagreements, so if you go to rpm.org/releases, it says 4.12.01. In the GitHub repository, it says 4.12.0, and Fedora is using 4.13.0, which doesn't seem to be an upstream release for it. Yeah. So status right now is one stack buffer overflow that I reported is still unfixed in the Git code. And in the release you can find, at least the ones you can find, maybe there's a secret release somewhere I didn't find, but in the release you can find all these bugs are unfixed. And there are more, and then some people kind of, there was a discussion on Reddit where someone said, this is all boring because this is all after the signature check. So I tried it again with pre-signature check and still found some things. I'm not really sure what to do about it right now because they seem not to be willing to fix the situation. So the thing here is these bugs are not that interesting. But what's interesting here is that the development process of RPM seems to be completely broken. Like, I mean, that's not how you do things. Yeah, we hopefully can agree on that. Yeah. And a small announcement here. There's a Berlin security meetup, and the next meeting is tomorrow. So if you're interested in security and cryptography, you may want to come. It's at the Mozilla Berlin community space. And that was my talk. Thanks for listening. Please test with Address Sanitizer and please use fuzzing to test your software. And now I'm open for questions.
It's more a comment again than a question. I'm one of the developers of Popular, the PDF library.
Oh, great! I want to talk to you.
I randomly get people saying, "Yeah, I have this PDF that crashes the thing." It's like,
yeah,
okay,
I did that. Yeah,
yeah, maybe. Then I say, "Can you report the bug?" And then like, no, because it's a security. And then we end up in the same situation you mentioned. Like, they don't want to report the bug because it's a vulnerability, but I want them to report the bug because it's much easier to track if it's in a bug tracker. So, yeah, I understand the thing you said, let's not discuss about it, let's just fix it. But sometimes it's like, they don't even want to give me the file to fix it because they think they deserve more things than using a bug tracker. I don't know.
So I reported a number of things in the bug tracker and they have not been fixed and it's more than a year ago.
Oh, so, really? Okay,
yeah.
Let's fix them now. Send me an email. No.
And also, the GNOME bug tracker has no option that I, as a bug creator, can create a security bug that's kept secret. The bug tracker has this ability, but I cannot trigger it. So maybe that's something. So maybe we should talk later because I think there are stuff that can be improved, and yeah.
One thing that I would ask you is, do you know of anything for actually fuzzing user interfaces? Because I mean, fuzzing file-based things is one thing, but user interfaces are also prone to, well, missing input validation, let's put it that way.
Yeah, okay, so first of all, you can just like use them. Or start them. Like, as I said, I started KDE and I think 4 or 5 different bugs just by starting it. What I did for a while was run my email client with Address Sanitizer enabled. The problem now is I know there's a use after free bug and I don't manage to fix it because it's like complicated, and now it's a bit scary because I know there's this bug. It may be a security bug, and so that's actually, but I think that's a good way to do it. Like if you're the developer, just occasionally run your application with Address Sanitizer enabled. And there has been some work done by LibreOffice where they simulate user interactions with a fuzzer, but I have not looked closely into this, but yeah.
So can any of these principles also be applied to, let's say, safer languages, just like Rust or OCaml?
Yeah. I mean, it entirely depends on the language. So what you can always do is these things like differential testing, where you're just doing some correctness tests that is like independent of any language if you have a function that produces wrong output. And there are all kinds of things to adapt AFL or similar tools to other languages. So I think there's an AFL Rust, and the OCaml people are also using it. I'm not sure how exactly, but I've been told so. And there's a GoFuzzer. The question there is, what are you looking for? So some of these safer languages can crash, like they crash if you have a buffer overflow. Some of them just like try where crashing is not really a valid thing. I mean, they can still crash when there's a bug, but there are all kinds of ways to adapt this to safer languages. But I think the thing is that the C has most of these crashing bugs. Therefore, there you get most of the output.
You mentioned that you run the Address Sanitizer on Qt. Did you also try fuzzing Qt?
No, not yet. I just did this in the past couple of days because I thought I have to do it for this talk.
One question, you mentioned these rare bugs in mathematical code, which is actually pretty typical. How does a fuzzer find that? I mean, if it's so unlikely that you really get the right input.
That's a very good question, and I hope I wished I knew the answer. So there are people kind of it would probably require some very detailed analysis of what's going on. My guess here is that AFL has a tendency to create repeating patterns, and that seems to be more likely to trigger these kinds of bugs.
Okay.
But there was, for example, a discussion I had with the developer of LibFuzzer because he was very angry that there was one bug that AFL could find and LibFuzzer could not find. And he said, well, that cannot be, and LibFuzzer is the better tool, and he fixed it now. And he fixed it by adapting this pattern generation thing that AFL does.
Because these are really horrible bugs that can live for 10 years or so. And nobody finds them. And this is where probably the symbolic analyzation really would help, right? Because it can analyze the mathematical structure of the code and then generate this.
So I had this discussion with people who are doing formal analysis and symbolic execution, and they said, yeah, our thing is good for finding these bugs. And I asked him how many bugs he has found with it, and he had 1. And I had like 5. So I'm not sure if this, maybe there's but I feel right now that fuzzing is at least produces more results.
But AFL isn't doing no analysis of the code at all, right? It just checks new code paths.
Yeah, that's its analysis it's doing.
So
it finds new code.
randomly find the correct number that then triggers this code path and this code path, blah, blah, blah.
Yeah. So I mean, yeah, maybe we can later have a discussion, but all this formal verification stuff, all this sounds very interesting, but then then you're not so impressed by the real results that are produced by this.
Okay, thank you.
I have one comment, like I'm one of the guys who actually tried to build all of the KDE and Qt applications with ASN, and I haven't seen your bug, so I was wondering whether that could maybe be due to me not compiling libxkcb or stuff like that with ASN enabled. Because like I'm not using Gentoo, right? I didn't rebuild all of my system.
So I think if you build Qt and KDE on top of it with ASN, you should find them.
Maybe it's new. Yeah. Thank you.
Hi, I have a comment from my practice, my job. We have commercial software based on open source components, so to say. Yeah. We use Qt. We are still at 4.8. Yeah. And I'm using Valgrind and Address Sanitizer for years. At the beginning, as we started using these tools, it took us a year or two to eliminate bugs from our software. And at the moment, the last, I would say, 4 years, I'm hunting bugs in libraries like libfontconfig or glib or something like this. And I'm not sure, should I really report all these bugs where I actually have only the stack trace and the place where it happened, and I don't really have time from my manager to look deeper into it. And so my job is limited to putting all these stack traces onto suppression list. So, yeah, suggestions?
I don't have a good answer to that. I mean, that's basically something you have to deal with the upstream projects if they kind of accept low quality bug report. I have a similar situation that I can run this Gentoo and try to compile all the packages with Address Sanitizer, and then I have a bunch of log files with Address Sanitizer errors, but like I won't ever like look into all of them. So I'm wondering if I should just put this online somewhere and have some crowd. So I don't have a good answer to you. Sorry. But I mean, ideally, these projects should at least all use some kind of Address Sanitizer testing themselves.
If there are no more questions, then please give a hand to Hanno. Thank you.